Hello, everyone. Thanks for joining us today for our webinar, What You Need to Know About Lambdas. My name is Laura Masterson. I'm the Community Manager here at TypeSafe. Just wanted to note a quick speaker change for today. Today's webinar will be led by Ryan Knight, Senior Consultant here at TypeSafe. Just wanted to go over a few housekeeping items before we begin the webinar. First of all, the webinar is going to be recorded, so if you need to hop off early and can't make the end, you can listen to the recordings later. And if you have any questions throughout the session, feel free to submit your questions in a chat box in the lower left-hand side of your screen. And I'll try to address those as we go through and save some of the good ones for the end where Ryan will do a Q&A. And so there are a couple polls that we've been running at the start here. Feel free to respond to those. I'm just giving folks a few minutes to join. Another poll here. What language are you using for development? All right. So with that, I'm going to hand things over to Ryan and let him introduce himself. I'm going to close this poll in a few moments. Thanks, Ryan, for joining us.
Thank you, everyone, for joining. Really excited to talk to you guys about Lambdas. Just to give you a little background about who I am. I'm a senior consultant at TypeSafe. I do consulting and training around the world. I do a lot around functional programming with both Scala and Java. I've been using Lambdas on the JVM for about 2 years now. So I have a lot of familiarity with Lambdas and the benefits and the challenges with them, and hoping to be able to teach everyone a lot about them. You know, and the greatest thing about Lambdas is it really makes you feel successful as a programmer. You know, it gives you this face of pure accomplishment. It really makes programming fun again. If you've been doing, Java, very imperative style programming, and it starts to feel very repetitive after, 5, 10 years, functional programming really brings a fresh approach to it and really makes programming fun again. So there's a lot of reasons why, let's see here. Get used to this. We're using a new conferencing tool, so I'm still trying to get used to it. So there we go. All right, so why do I love functional programming? There's a lot of reasons why functional programming has a lot of strong benefits. And one of the first things is the immutability. The idea of functional programming is you want to avoid state and mutable data. And instead we wanted to start looking at everything and seeing if we can make it immutable. So we want to write functions that depend only on the inputs and not on the program state. So we want to avoid, any kind of external global state and have more pure functions. The other advantage of functional programming is what's called referential transparency. What this means is that a function can be replaced with its value without changing the behavior of the program. And so the idea is in functional code, right, if you have something that outputs as the value of a function depending only on one argument, right, and those arguments are the input to the function, so calling a function twice with the same value will produce the same result both times. And because it produces the same output, right, it can be replaced with the resulting value. So that's referential transparency, is where we can replace a function with the resulting value, and it's not going to change the program flow. The other neat thing with functional programming is it makes functions first-class citizens, where we can pass functions as to methods, we can pass functions around, we can return functions. And this really allows us to start treating behavior, right? We can start treating our behavior as a method argument. So we can start passing the functions to our methods. We're passing our behavior to our methods. And the other thing it does is it eliminates the side effects. So if we're not dependent on the state when we call a method, if we're not dependent on global state, we're really isolating the state to the input and the output of the function. We're eliminating all the side effects. And that has a lot of benefits in terms of making the program easier to use, easier to read and understand. It also makes it easier to test. So why would we want to do functional programming? What are some of the core reasons for functional programming? And one of the biggest benefits, and one of the reasons we're most excited about functional programming, is it's really the foundation for what we call reactive programming. So at TypeSafe, we've developed a reactive manifesto, and we're advocating a new type of architecture called a reactive architecture that's based on handling events and breaking things into asynchronous computations. Well, to handle these events and to handle asynchronous results, we want to avoid using inner classes. We want to make our callbacks like small snippets of expressions that can be easily called and passed around. And so the traditional approach to this was to use, Java inner classes. An inner class had a lot of boilerplate code that was hard to read, and it was hard to reuse. And Lambdas really solved this problem by avoiding these inner classes. And so it makes the programming model a lot more concise and cohesive. The other benefit of functional programming is it provides a higher level of abstraction. So we want to look at the what and not the how. So we want to kind of look at a program at a higher level. So let's talk a little bit about how we can do that. So if we look at traditional Java code, it takes what's a very imperative approach. Right? So in this example, right, we're defining our list. We're defining an empty list that we want to put the changes to our list into. And then we have to define how to iterate through the original list, define the operation, and then define how the new list gets built. So we're having to do a lot of explaining, in terms of primitive constructs and loops of how to do something. Well, instead what we want to do is we want to do something that's a very declarative approach. So declarative approach to the code, is we want to remove the temporary lists. We want to have to remove, creating a temporary list and adding to it. We want to remove the looping and thinking about, how we loop through our collections. And we really want to focus on the what, of just, incrementing that number. And the way we can really do this is using lambdas. So what is a lambda? So in this presentation, I really want to focus on the general concept of a lambda, right? There's different implementations in different languages, which we'll cover, but they all have this very similar concept of a lambda. And you can think of a lambda as a function literal, similar to like a string literal where we declare our string value as a fixed value in the code. We can declare a lambda as a function literal, which is a fixed value in our code. So it's not binding that function to a variable name. So it's only used in the context of where it's defined. So it's considered an anonymous function. And this is really one of many possible ways of implementing functions in a functional programming language. So and we'll take a look at some of the different ways of implementing these lambdas. But really you can think of it as it allows not only values to be passed around, but also behavior to be passed around. So we want to change our code from doing and the other thing it really can change is from doing an external iteration on our data and defining how we modify the data from loops to doing an internal iteration. Now I'm going to show how that works with Java 8 lambdas. So first to just give a little bit of background on Java 8 lambdas. The way they work, and most people have probably seen these by now. The way Java 8 lambdas work is basically you use a functional interface that defines a single abstract method. And this single abstract method is the target type of the lambda. So when the Java compiler compiles the lambda, it looks at this functional interface for the target type. And in Java 8, they've defined a number of functional interfaces in the Java util function package. So there's a lot of standard functional interfaces in there. So for example, one of the more common ones is a function. So here you can see this interface. It's defined as a functional interface. It's marking it as a function. Right? It has a single abstract method. And this is the type of this will be the type of our lambda, the target type of our lambda. So here it's just applying the type T, which is the type of our input, and it's returning a type R, which is the type of our output. And so in Java 8, now we can use this target type to declare an anonymous function or a lambda. So here's an example of using Lambdas in Java 8. So here we've declared a array list, right, 1, 2, 3. And then what we're going to do is we're going to change it into a stream. So streams is another new feature of Java 8. And the way you think of streams is they're not a collection. They don't have a storage for the values. They're really just providing a pipeline of manipulating your data. So they're very functional in nature. And what they're going to do is they're going to produce a result. It doesn't modify the underlying data source. What it's going to do is it's going to manipulate the data as it flows through the stream and return a new collection. And what's interesting about streams in Java 8 is that they're lazy. So when we do an operation on them, we might not actually end up going through all the values. We're only going to go through as many elements as we need to get to a final answer. And the other interesting thing about streams is we don't have to define the bounds, right? So we can actually treat streams as almost like an infinite stream, and we're going to let the client consume the values until they're satisfied. So it's going to just go through and process all the values until that stream is completed. So in here, we could we convert our numbers into a stream. We're making the numbers basically a stream of integers that we're going to process. What we're saying is we want to map those streams, and we want to map them to a new value. So we want to take each number in that stream, and we want to add 1 to it. And if you look at the definition for the method map, it actually takes a function interface. So in this case, it's basically implementing the function interface of an integer to an integer. And so what this is going to do is it's going to take that stream, it's going to add 1 to each of the numbers, and then when the stream is done, it's going to collect all the results and convert it back into a list. So that's how it's done in Java 8. This exact same concept can be done in a number of different languages. Scala has a different approach to how it implements lambdas, and it actually has a function type in the language that's used to represent the lambda. So for example, like map, you could think of map as being a function, again, a function that takes an integer and returns an integer. In Scala, what it does is it uses the equals arrow to declare it as a function. So here we've declared a function in our method signature of an integer that takes a function that takes an integer and returns an integer. And how Scala implements that underneath the covers is it actually creates a functional implementation. So then if we look at lambdas in Scala, right, it's fairly similar to what we were seeing in Java. The difference is we don't have to convert our list to a stream first. Scala by default treats everything in a manner fairly similar to streams. So we can just take our numbers and we can say map on the numbers. What Scala will do is it's going to do an internal iteration on that list for us. And for each number, it's going to add 1 to the number and return a new collection. And so what map does is it takes a function, and here we're declaring a lambda or an anonymous function of incrementing each number by 1. So this lambdas is actually very popular. It's becoming a lot more popular in a lot, and it's in a lot of different languages. It's actually been in JavaScript for a long time. People just really haven't thought of JavaScript as having lambdas, but really what it is it has this same ability of declaring lambdas as anonymous functions. So here's an example using Nashorn on the JVM. And with Nashorn, we can use the Java collections, right? So here we're declaring a Java array list. We add 3 values to it. Right, but the difference, one thing we're doing here is we're going to make this into a parallel stream so we can process it in parallel. And we're declaring the anonymous function to add 1 to it. And then we're also declaring the anonymous function that's going to push all the results into the result array. The same type of concept can also be implemented in Clojure. Clojure has a slightly different syntax. Right? The interesting thing with Clojure is that it uses a prefix notation, so you actually read it backwards. So here we declare the list 1, 2, 3, and then on that list we're declaring map. So we're saying map on that list. And then again, because it's a prefix notation, right, we're declaring the operation we want to perform. We're declaring add 1 to each element. And then the final part of that statement is print line. So what it's going to do is it's going to take those results and it's going to do a print line. The other thing with Clojures is that it's lazy. So what that means is it won't actually evaluate this line until we call print line. So it doesn't actually do the evaluation until the results are needed. So in this case, we put in a print line to force it to do the evaluation. Right, we can also do the implementation in JRuby. Ruby's had this concept of Lambdas as well for a long time. Right, with Ruby, it does something fairly similar. Right, we have a list, and we're adding 1 to each element of the list. What's different about Ruby is it actually uses mutable data structures. So in this example, it's not actually returning a new list. It's actually mutating the original list underneath the covers and adding 1 to each of those. So this looks nice. This looks like a lot better syntax than what we're used to. This is a lot easier, than the imperative approach of having to figure out how to, iterate over our numbers, and get each value and increment it and then store it in a temporary value into a new temporary list. So this is looking nice. Lambdas have a very nice syntax, and they seem really powerful. The problem is there is some problems with Lambdas that we want to talk about, because although this all sounds nice and wonderful, there's some issues. So what is this problem? Well, there's some real caveats with Lambdas that we want to talk about. Right? At first glance, we think this is great. We're able to do things in a lot easier fashion. It makes our code a lot more compact and easier to read. But there's some downsides to this that if we're not careful with using our Lambdas, that we're going to get into trouble. So let's go over some of those problems and talk about what we need to think about when we're using Lambdas and some of the cautions we need to take. So the first problem with the Lambda is they're an anonymous function, so they're limited the scope to their call site. And because of this, you can't reuse their functionality elsewhere. Right? If we declare this anonymous Lambda, we're not going to be able to use that same anonymous Lambda in a different method for different calls. Right? The other problem with a Lambda is they're not testable in isolation. Right? So if we have a method that has a Lambda in it, right, we might be able to test that method, but we probably aren't going to be testing that Lambda inside of the method. Right? And the other problem is, right, if there's no identifier to that Lambda, there's no way of testing the Lambda individually. Right? So what often happens is, when you have code with Lambdas, people will write tests that seem like they work, and they often forget the edge case of testing the Lambdas that the code is using inside. And so the only way of testing those is by writing more tests for the enclosing methods. So we end up kind of having this problem of figuring out how to test our Lambdas. The other problem is maintainability. Right? There's no description in that Lambda. So if we have this anonymous function that's adding 1 to each element, well, there's nothing that's describing what that function's doing. So you have to read through the entire Lambda to figure out what is going on, and you have to try to figure out what it's doing inside. And they're also more complex, right? And as you get more and more complex Lambdas, this gets harder and harder to do. So they really become they can kind of be a waste of valuable development time because of these problems. So an example of anonymous Lambda, the problems of anonymous Lambdas, or anonymous functions and Lambdas, is this. This is something that we see in Scala code, which is, right, we have this outer anonymous Lambda. Inside it has Lambdas, and inside that it has Lambdas. So we've got this triply nested Lambdas. Well, this type of code is going to be really hard to test. It's going to be hard to maintain, and it's just hard to understand. Right? So, we write it, we understand what it means. All the other developers who come through and look at it, they're just like, what is going on? They have no understanding of the meaning of this Lambdas or how it's working. All right, there's the other problem with anonymous Lambdas is they have lousy stack traces. The reason for this is because we aren't creating a separate method with a given name, right? we're not calling a particular method. What the JVM is doing internally is to make it run on the JVM, it has to do what's called name mingling. It has to create a internal representation for the lambdas, come up with its own kind of name, kind of anonymous name. So when we look at the stack traces of these, we're going to be able to tell very little about where the problems occurred. So this makes it really hard, especially when you're in production, you're looking through your log files, and trying to figure out where the problem's coming from. This name mingling is going to cause a lot of problems of being able to understand and track down where the problems have originated from. So let's take a look at some of these problems. So first in Java 8. Right, so as an example, I divide by 0. I have this anonymous lambda that's dividing by 0. Right, it gives me an arithmetic exception. If you look at the stack trace, it says lambda dembo, lambda $0. So what it's done is it's taken this anonymous function and it's named it $0. So when I look at my stack traces, and you can imagine in a larger production code, if you end up with these kind of lambda zeros, you're not going to know where the problem is coming from. And especially if you have multiple nested lambdas that are all on the same line, it gets harder and harder to tell which of the lambdas is causing the problem. And so this is a problem that's not specific just to Java 8. It's also a problem with every other languages as well. So for example, if we run this in Nashorn on Java, right, with the JavaScript, doing anonymous lambda, we divide by 0. We get some pretty interesting output. JavaScript actually defines the value of something divided by 0 as infinity. So, so this anonymous lambda is actually going to add infinity to our new collection. So yeah, JavaScript has some really interesting behaviors when you start doing anonymous functions and trying to figure out what's happening inside of these anonymous functions. So the best description of JavaScript, there's this really great tweet about JavaScript. It said, JavaScript doesn't have a dark side, but it does have a dimly lit room full of angry clowns with rubber mallets. This really describes kind of the problems with JavaScript, of trying to deal with JavaScript. It makes it very difficult to deal with. It makes it really easy to write, your basic programs. And when you get to these more complex enterprise-type applications, especially with anonymous lambdas or anonymous functions, it gets really hard to try to debug and figure out where your problems are coming from. So Scala, it has the same type of problem. What Scala does is it actually takes that anonymous function, and it's actually creating a synthetic class underneath the covers. And so what it ends up in the stack trace is we get this anon fun pound 1. Again, it's going to be really hard to find our problem and debug it. Clojure doesn't do much better. Clojure generates this fairly large stack trace, making it really hard to figure out where our problem is coming from. And actually, the one language that does a really good job of this is JRuby. And JRuby is actually able to generate a semi-decent stack trace, but the way it does that is it adds a lot of runtime overhead, because what it does is it actually captures the exception and makes it into a nice stack trace that you can read. So it's actually manipulating the stack trace to make it readable, but that's going to add some overhead to our runtime. So the last problem, one more problem that we have is difficulty debugging. So debugging on the JVM is getting better. Both IntelliJ and Eclipse are adding things to debug lambdas. Scala ADE has added the ability to debug into functions, anonymous functions. IntelliJ has added smart stepping to be able to step into your lambdas. But the problem is you look at these lambdas in the debugger, you're still not going to be able to tell the results of the operation. You don't get you don't get the full information of the stack, and you're kind of limited in your ability to step through these things and see exactly where the problem is coming from. And really, the biggest problem of all of these anonymous lambdas is something called closing over state. So a slight digression of what we mean by closing over state. So when we close over state, that's called a closure. And what that means is that we're capturing the state from the outside of the enclosing scope. So when we have this anonymous function, if the anonymous function is referring to a variable outside of the outside of it. So like in this case, when we do a map, if we do a map of a number plus x, right, the x is actually declared outside of the anonymous function or the lambda. And so it gets closed over and captured. Right? And so that becomes part of that anonymous function is that outside state. Well, the problem with closing over the state like that is that, right, that's variable that it's referring to can actually be a mutable variable. So we could close over, say, for an example, an object, and even though that object might be declared final in Java, right, what's inside of that variable can change. So for example, if we have a collection, we could close over the collection, we could capture that collection, and be expecting some particular values, but when we go to actually operate on those values inside of that lambda, we're going to find the values could have changed. So these are a lot of the problems with having these anonymous lambdas. So it's a very nice lightweight syntax. It looks nice at the start, but it causes all of these problems. And so we want to come up with an easy way to solve these problems. And the solution is actually fairly simple, and that is avoiding lambdas by doing named functions. So what this is going to do is we're going to, instead of using anonymous functions or lambdas, we want to make these functions named and reuse them throughout our program. So we'll have something that's a lot more maintainable and easier to understand in production. So what do we mean by named functions? Well, basically the idea is something where we can give a function a name, and then we pass that name around. And what that's going to do is it's going to help the compiler to be able to generate a better stack trace, and it's also going to be able to help with debugging. Let's take a look at some examples of these named functions. So the first one here in Java 8, right, we can do a named function in Java 8. We're going to name our function add1 to value. Right, it's just a number that returns a number. And here, we're doing the number divided by 0. And now when we do our map, we do a add1 to value. So what that's going to do is that's going to call that function for every value in our map. The nice thing with these named functions is we get a slight improvement to our stack traces. Right? So we're able to improve it a little bit. We're able to see, get a little bit better reading on the line numbers, but it's still not perfect. We're still getting this kind of anonymous syntax, and we're still getting some problems with being able to read the stack traces. So let's improve this even more. And the way we can even improve our stack traces more and make this even easier to debug is what's called lifting. So what we can do with both Java 8 and Scala is we can lift a method into a function. So what that means is that when the function is expected, so it's expecting something like an anonymous function or implementation of a function or a functional interface, we can pass in a method. And even though that method is not an anonymous function or declares an anonymous function, it's going to change it into a function and be able to pass that in as the method argument. So really the only thing that is required is that method must meet the contract of the Lambda. So if we have the function, like if we look at the Java util function, right, it has an apply method. So the only, right, it has an apply of something that takes an integer and returns an integer. So we just need a method that takes an integer and returns an integer. So let's look at some examples of how we can do this with Java 8. Right, so instead of declaring a function with and giving a function a named function, we're just declaring a method, add1 to value. Right, this add1 to value just takes a number and returns a number. And now we can call this, right, we can just say map. We have to give the name of it. We can use a method reference, a Java 8 method reference, where we're basically just saying, what the name of the class is, where the method is found, and the name of the method to call. And we don't have to declare the variables to pass into the method or how to use the return type. That's all part of the map operation. So what map is going to do is it's going to call our function, our method for us, and it's going to pass those values into that method, right? And then it's going to add the returns results to the stream of the new values, right? So it's going to basically stream the results back into a new stream that we can then end up collecting into a new list. And the advantage of this is we get a much better stack trace. So here we do a bad examples, right? In this bad examples, right, when we say add one to value, well, we get the actual name of the method and the actual line number where the problem is coming from. So this allows us to be able to find our problems a lot easier, especially in production. This is going to be extremely valuable so that we can debug and find our problems a lot easier. The other advantage of this is obviously that in a IDE, we can step into the method and actually look at what's going on. The same thing with Scala, right? With Scala, you can declare anonymous functions. Here, we're declaring an anonymous bad function. That's something that takes an int and returns an int. The problem is that we've declared our function as a def. So we're saying def bad function is equal to, and it's going to create a new function every time it gets called, right? And so we still get this funky stack trace where we can't read it. So one clarification on this, when we say def like this, def is not stable, meaning it reevaluates it every time it looks at it, every time it gets called, right? So every time you use this bad function, it's going to return a new function. And that's why it's better to stick with a simple syntax of just using a direct method declaration, right? And so instead of declaring bad function as something that returns a function, we're just going to make a standard method call, a method called bad function, and Scala will lift this into the function for us. And the advantage of this is we get a much better stack trace. So here, if we look at using this, right, so we've declared the method bad function, and when we do a map on it, you'll see that the stack trace, we actually have the name of that method. And so this is going to make it a lot easier to find our problems, and also makes it a lot easier to debug. So really, I'd like to summarize what the advantages of using method lifting over lambdas. So just to clarify, kind of as a summary, a lambda is basically an anonymous inner function that's not named and is not something that we can step into or reuse. By making these methods and taking these anonymous functions and putting them into methods, well, now we can reuse the method. We can test that method independently. The other benefit is that you cannot close over variables. All right, so if we go back to the Java 8, right, we had this static method add one to value. Well, there's no way for that method to close over the state, right? So it's only going to operate on the parameter number. I should say, I guess if you had a global variable, you could use a global variable and close over the global variable. That would be bad. But the idea is if you use these methods, you're much less likely to close over the local state. And then they're going to be much more testable. So their independent methods are going to be testable. They also have a name, so they're much more descriptive. So you can say, this is add 1 plus 1. And so someone looking at this, it helps them to understand what is the benefit of this method. What is this method doing? So I'd say this is some general rule of thumbs. Is we want to reserve Lambda usage for the most basic expressions. Expressions that are very simplistic, that aren't going to have cause a lot of problems. Especially if the Lambda has side effects, or is calling external services, you really don't want to use a Lambda for that. You'd want to use that as a method. Anything more significant than that, anything that's very significant, we want to take out of our anonymous functions, take out of the Lambdas, and put into these methods. So at the start, I mentioned how we're excited about functional programming in general. We're excited that Java 8 has it's introduced Lambdas, it's introduced functional programming, and the benefit is we can start doing more reactive event-driven programming. So I wanted to just kind of look at a little bit of how we can do that with Java 8, and the benefit for doing what kind of benefits we get. So Java 8 added something called the futures, right? So sorry, completable future. The difference is from a normal feature, right, with the old Java Futures library, there's no way of adding a callback. So you create a future, you'd have to have some kind of a variable that waiting for the value to come back in, and you'd have to have some kind of a locking or synchronization block to say, when this future completed, then go and check this value. Well, with Java 8, instead of having to deal with mutable state and synchronization code, what we can use is something called a completable future. And the idea is simply that we are going to add a callback to be specified as a function when that future completes. So like this example, right, we have a completable future, and we're going to give it a supply async. So what this is the async method that gets called when this future completes. And the idea is that we're going to create a cache retriever. It's going to go out and get a customer out of the cache and retrieve that customer and bring him back. And then when that future completes, right, we can have it call this method. And the other thing that that's neat with the futures is you could have multiple futures and chain them together. So we could have a future that goes out and checks the cache, a future that goes out and checks the database, and then we can bring them both back in together and decide whichever one completes first is the result that we're going to return. So with this completable future, we can now add callbacks and asynchronous values that get called when they complete. So a question that always comes up, when we're talking about Java 8 Lambdas and Scala, people always ask, what are the differences between Java 8 Lambdas and Scala? So I just wanted to kind of touch a little bit on the differences between the implementations. And these are really just implementation details. Right? One of the big differences is Scala is that functions are first-class citizens. So, so there's actually a function type in Scala. The Scala compiler can infer the type of the function. So, it does the Scala compiler has a very powerful type inference, and so you could declare a method or a variable to take a function or return a function, and then when you call that or use that, it's going to be able to infer the code as a function. With Java 8, it's a little bit different, and what it's really not treating functions as first-class citizens. Instead, it's mapping them to a functional interface. So it has so what it's doing is a weaker type of inference, right? It can only infer the type based on the left-hand side of the assignment operator, right? So we're going to, if you have a named function, you'll give it a type, like the function, that takes an integer and returns an integer, and it will be able to infer the type of the anonymous function on the right-hand side based on that type inference. All right, the other difference is in the implementation. So with Scala, we're still targeting Java 1.6, which means that we don't have the advantage of a lot of the newer features in the JVM. And so the way that Scala implements functions underneath the covers is it creates a synthetic class to represent the Lambda. Right, so it does create some more bytecode. The difference with Java 8 is the language creators were able to really kind of take advantage of the JVM and the features inside the JVM and really target Java 8 specifically. And what that means is they can really leverage something, the new instruction that came with Java 7 called invoke dynamic. And what that does is that allows you to avoid creating synthetic classes. There's a fairly good blog post that kind of used the Java P to look at the actual bytecode that gets generated from both Scala and Java 8 Lambdas and kind of compare how the implementations work. So there's this implementation detail in terms of what happens underneath the covers between Java 8 and Scala. So in summary, what we really like to see in, going forward in the future is, people who create these languages and the tools to work with these languages need to, we're hoping to continue to push the envelope and, continue to add new features and functionalities to make working with Lambdas easier. Scala, at TypeSafe we built the Eclipse-based Scala IDE, and that has, a lot of Lambda-friendly features. For example, you can, smart step into your Lambdas. You can, debug into them. IntelliJ added in IntelliJ 13 for Java 8, it added the smart step into, which allows you to step into your Lambdas. there are still the downside is that when you look at your stack and you look at your variables, you don't see the full information that you would in terms of a normal method call. And so there's still, even though the debuggers help, there is still all these downsides to the Lambdas. So let's go to questions now and see if anyone has any questions about Lambdas that we can answer.
Sure, thanks, Ryan. There are some great questions here. So I can kind of go through them and pick some good ones that would be good for everyone to hear. So the first one, from what I understand, in Scala map returns a collection, but in Java streams it's returned M. Is that correct?
Yeah, I'm not quite sure what that means.
Yeah, maybe.
If he could update his question to clarify. So the Scala map, let me just explain that. So the Scala map, what the Scala map does is it basically returns the same type of collection. So whenever you pass in a collection, like a list or a vector or a set, it will always return that same type of collection. So that's a little bit different than how it works in Java. In Java, what you have is you have a stream, right? And so when you do a map on that stream, it's going to basically return a new stream. And then on that stream, you do a collect. And you can actually change the type in that collect to do a different collection type. And in Scala, if you want to map from one collection type to another, you have to actually do a conversion on that type. So hopefully that helped answer that.
Yeah, hopefully, and if not, then please just resubmit the question, and we can add some more clarity. So, second question. This is from earlier on in your presentation, Ryan. So we might have to go back a bit. So, is there no way in Java 8 to assign a lambda to a variable?
Oh, right. So I did answer that one as I went through the presentation. Yeah. So yes, you can assign names to Java 8 lambdas. And I also saw this question in here: do all Java 8 lifted methods have to be static? And the answer to that is no. You don't. The methods don't have to be static. They can just be a normal class method.
Cool. So there's a attendee that's just wanting you to add a little bit more detail around lifting. Can you elaborate a little bit more on that section of your slides?
Yeah, the idea with lifting is when so you have a method or like you're calling a method like map that's expecting a function. So in Java 8, you'd have it's expecting it. Here, actually, let me, I can probably pull up. Can I share my screen, Laura? Would that work? And I can kind of show.
Yeah, you can. There's a little share desktop icon at the top, and you can just click that, and we'll be able to see your screen.
All right, let's see. Let's see. So Laura, can you see it says IntelliJ IDE?
Yep, I can see everything that you're doing on your screen right now, and it seems to be, the text seems to be large enough if my screen's expanded. So I think everyone should be able to see what you're working on.
Okay. So to kind of explain a little bit about lifting, if we look at the map, right? So we did the numbers.stream.map. So what map, so we talked about how map is going to basically do a operation on each element of the list. If we look at the definition of map, map takes a function of type T that returns a type R. So it's basically expecting T as the input and type R as the output. What the function is it's the Java util function interface. It has a single abstract method apply. Well, so what this is this method map is expecting an anonymous function or a lambda, And to fulfill that, we can declare an anonymous function or a lambda, or we can use a method. So here, where we're doing, x is, x plus 1, instead of, doing the anonymous lambda, I can use this method I have up here of add 1 to value. And then I can declare it as a method reference. And in this case, right, because I'm using method reference, it's requiring it to be static. Right, and so here map is expecting an anonymous function, and then I'm giving it a method. And so what it's going to do is it's going to lift that method into a function. So it's going to basically convert that method into a function for me and make it, and then call that method for each time it goes through, each element of the list, as it would an anonymous function or lambda. So what's the next question?
Sure. So let's see here. You showed how typical Scala code tends to look like several levels of lambdas. Did you find a preferred level of nesting or some kind of coding convention which would make a typical Scala code more readable to newcomers?
Yeah, in terms, my personal preference is, one level of nesting is probably the most you'd ever want to do. Especially if you have a group of mixed Java and Scala developers who, are going to be, the Java developers are going to be trying to get their head around the Scala, trying to understand what's going on. When you have multiple levels of nesting, it's really hard to trace through and work with that code. So at most, I would say, one level of nesting, just to make it easier to work with.
Mm-hmm.
And really it's about, trying to make the, a lot of people try to, they like to see, how compact they can make their Scala code and make everything, on one line. That's fun for, maybe, coding competitions or, competing with your coworkers and seeing who can make the most compact code. In terms of production, readable code, that makes it really hard to, if someone comes back in, a couple of weeks later, a couple of months later, they see these deeply nested structures. It's just too hard to understand. So that's why I personally really recommend trying not to do that.
Okay. Let's take a couple more questions here, and then a lot of these might be actually suitable for you to follow up with directly, Ryan. We can go into a little bit more detail over email. So next question, can we invoke a method asynchronously in Java 8 with lambdas like the one similar in JavaScript?
Yes, yeah. Actually, the example I was showing with the Java 8 and was on Nashorn. And it was actually using what's called parallel streams. And parallel streams are actually going to be part of the core Java 8 collection, or the streams library. And what parallel streams basically does is it tries to asynchronously process that stream. In other words, it breaks the stream up and says, oh, we can probably do this map on different parts of the stream at different times, and so it makes it asynchronous. So yes, there's a lot of different ways of kind of leveraging that asynchronous stream processing in Java 8 directly.
Cool. Next question.
So I can answer
what is your? Oh, yeah.
Go ahead.
Go ahead. I was just looking at the
questions. Yeah.
Mm-hmm.
Well,
go ahead
what's
if there's
the next
one
question?
that jumps out to you.
Sure. So when will Scala use invoke dynamic? Will they continue to provide JDK 6K compatibility then? So that's something we're really looking at with Scala 2.12, and we're trying to figure out what our user base is using. The hard part is we have somewhat limited resources on our Scala compiler team. We were talking about maybe a flag that targets, if you're on Scala 2.12, you can put in a special flag to generate code that leverages Java 8 invoke dynamic, makes tighter bytecode. The problem is then we have to support two different types of bytecode generation. That's a lot for a small company to support. So we're trying to figure out how we're going to do that. We might, the hard part is that we still have a lot of companies on JDK 6. We also want to support Android. And so if we move to Java 8 and the invoke dynamic, we would leave a lot of customers unsupported, which is a tough path to go down as well. So we're still trying to sort that out and figure out what the path forward is. And if you have an opinion, and your company is, say, using Java 1.6 and you want long-term support for Scala, it'd be good to hear from you about that. So.
Great, Ryan. You would maybe take one or two more questions. I don't know if there are any others here that would be helpful for everyone to hear on the recording, and then we can wrap up.
Yeah. How does Akka feature in Java 8 differ? Right. So yeah, that's a pretty big question in general, right? So this Scala does have futures. So there's Scala futures. There's Akka has actors, which are used to do concurrent programming as well. And then there's Java 8 completable futures. Java 8 completable futures are fairly similar to Scala futures. Java 8 futures and Scala futures both wrap the internal Java util concurrent toolkit underneath the covers. Akka actors are actually a completely different paradigm that aren't doing futures. Instead, they use actors, and they use a message passing paradigm to do the concurrency. So instead of creating a future that's run in the background asynchronously, you're actually running an actor in the background and sending it messages and telling it how to do its processing. So.
Cool.
Good?
Oh, no, you go ahead.
There's a question, does the name mangling also happen with anonymous classes, right? Yes, that's true. Yeah, the name mangling problem has happened with anytime you have an anonymous function or anonymous class. So, do you see any other questions, Laura? Or?
I think a lot of these might just either need to be passed along to some people on the Scala team, or we can follow up with them via email and just elaborate in more detail. So thank you, Ryan. That was a great session. I hope everyone enjoyed it. There's been quite a few questions here about whether or not this webinar has been recorded and if we'll make the slides available. The answer to that question is yes, on both fronts. This session was recorded, and we're going to be sending out an email to all registered attendees with the slides and the recording shortly. It usually takes us about a day just to do a little bit of editing. So look for that, and the recording will also live on our YouTube channel. And I wanted to just, on a final note, if you have suggestions or requests for future webinar topics, we do these monthly, so we're always looking for ideas from our community about what you'd like to learn about, who you'd like to hear from, and we want to continue making these successful and enjoyable for you. So if you have any ideas, feel free to email me. My email is laura.masterson@typesafe.com, and we'll do our best to schedule a future webinar of your choice in the future. And yes, so thanks, Ryan, for joining us, and we hope to see you all on future webinars.
Thank you, everyone, for attending. Let us know if you have more questions.
Okay, bye-bye.